and I'm going to be talking about using discrete event simulation for capacity planning at our Fetal Diagnosis and Treatment Center and how these tools can be used for to help inform policy. So the background, discrete event simulation is a computer simulation model of complex systems. It can be used to build models in silico of clinical and healthcare delivery systems, which can then be used to examine the ideas of what-if questions and consequences of change prospectively. Our Center for Fetal Diagnosis and Treatment is a 11-bed unit, 11-bed inpatient unit, which also has on the outpatient side where we see mothers with known fetal anomalies and can perform interventions, either surgical interventions or monitoring of the pregnancy through to delivery, at which point the infant may have immediate surgeries. So the question is, this has been growing at approximately 17% per year over at CHOP, and what we want to know is, when are we going to run out of space? How much inpatient space do we actually need to fulfill our demand for 5 years? And can we use this tool to make data-driven recommendations for evidence-based policy decisions? And this work was funded through the Implementation Science Working Group in the Department of Medical Ethics and Health Policy. So building a discrete event simulation of a clinic is essentially a 4-step process. You decompose the clinic into its constituent elements, the entities, these are the patients, paper records, maybe phone calls, everything that we do work on. Resources, that's us and other and healthcare providers. I'm not a healthcare provider personally, but it's the people who work in the clinic in order to perform the work that needs to be done, locations and paths, and then we build the flow modeling. And the flow modeling for a system like this essentially answers the question, how do entities consume resources at locations and then proceed to the next location? Similarly, there's also the flow of, if I am a healthcare provider, how do I decide from what task to the next task? How do I decide what I do next? Once we have developed this entire flow model, then we code the system into a off-the-shelf discrete event simulation software, of which there are many. We use MedModel for this, but I don't specifically endorse them. And finally, we need to validate the model. Once we've built a model that mimics a system, how do we know that it does what we think it does? Well, validation actually has sort of 5 methods in the best practices. We use 3 of them here. Face validation basically means you take your model, you show it to the people that work in the system, and everybody can critique it and agree that it does in fact accurately represent what they do in the real world. Internal validation or verification is what we do to go through the model, make sure our code works. We also do system stress tests where we will overwhelm the system with arrivals and make sure that the queues still function properly. And then external validation. External validation says, when provided with real-world type inputs, does the model produce real-world type outputs? The other 2 types of validation are cross-validation, which says if I have 2 different models, do they both agree with each other? And then predictive validation, which is what we're aiming for, which says when we make a prospective change in simulation and then make the same change in the real world, does that happen in real life? So the simulation, hopefully, is running. Simulation, resume. And what we see here are, on the left is the blueprint of our physical space where patients arrive and go through our inpatient and outpatient processes. They'll have surgeries and C-sections up above. Here on the right is the number of patients that are in our queue that are at home in the middle of a complicated pregnancy. They will be followed and tracked at home throughout their pregnancy and return to our outpatient side many times. They may come to the inpatient side to have surgery and then again later to delivery, for delivery. And we follow each individual patient throughout their course of care. So our validation, oops, let me come up here. This is just one example graph of our validation. On the bottom in blue, we see the real world. This is our inpatient days, number of patients in bed by day over the previous approximately 2 years. And above in red is our simulation data. We found no significant variation, no statistically significant variation between the 2 midnight censuses by day over a 2-year period. Now, of course, you can never use a statistical test to say that these things are the same, but we say we have no evidence that they're different. which suggests, along with additional validation techniques, that our model is ready to be used for experimentation. So in order to experiment with these, we build a control simulation. We have our validated simulation. We keep it simple and controlled. Then we perturb one aspect of the simulation and conduct a number of simulation runs using independent random number streams, collect data on our metrics of interest, and then do traditional hypothesis testing, just like any scientist would, where we determine, based on the change we made in the simulation, do we see a significant change in, for example, our midnight census over the course of the period of time. So, by way of conclusion, we can create these simulations and validate them, accurately capture current system performance, and then, based on, for example, increasing the number of rooms, we can determine how likely we are to be able to, going from 11 beds maybe to 13 beds, not run out of space between now and 5 years from now. Thank you very much.